Well, at this point, we have a pretty good idea of how materials behave under stresses that eventually cause deformations which lie in the elastic deformation regime. So now the extent of that elastic deformation regime eventually ultimately depends on the type of material that we're looking at. If it's a very soft material, like this rubbery piece of polymer that I have in my hands, then the extent of that elastic regime is quite large. Now, on the other hand, if I take a metallic specimen, and here is a paper clip, well, if I apply some reasonably small deformations, then the paper clip will always keep returning to its original location. But I know that if I ultimately apply a sufficiently large amount of stress, there will be a permanent deformation. Now, therefore, there is always a limit to the extent of the elastic regime, and something happens when you reach the limit of that regime. Now, what might happen is, for instance, for a metallic specimen, it might permanently deform. So in other words, it yields. In other words, there are plastic deformations. Or if this were a glass rod, if I bend it a lot, it will simply break. In other words, it will fracture. So our goal is to eventually estimate when we are about to reach the border of the zone to elastic deformations. Our goal at this stage will not be to predict what happens beyond that. I will have an idea as to what happens. For a glass-like material, probably it will break. For a material like metal, like steel, aluminum, for most of them, it will yield considerably. But I am not interested in the mechanics of how it breaks or how it yields. Not at this stage. These are going to be topics that we will consider in the future. I only at this stage want to be able to predict the stresses at which elastic deformations end and something else is going to happen. So our goal is to predict failure. And by failure, presently, we mean only two things, yielding and fracture. And if the stresses or the loading is such that it's uniaxial, a simple test can easily provide us with the information, the material parameters that govern yielding and fracture, but making use of those material parameters eventually in a multi-axial scenario is not trivial. So in other words, really the challenge in predicting the extent of the elastic zone, in other words, when yielding or fracture might happen, eventually is challenging under combined stresses or multi-axial stresses. And we're going to highlight that difficulty in a second. Okay, now at this point I should also highlight once again, well, suppose I have a piece of metal and I predict that it's going to yield, and the question is, well, it's going to permanently deform. How much will it deform? Or if I want to permanently deform it to such an amount, how much force should I apply? That's going to be the concern of our next topic. Now, if I have a brittle material, it might fracture. How does it fracture? What are the mechanics of fracture? That's going to be the topic that follows that one. So presently, what we understand is here we have two specific types of materials. One that is idealized as being ductile, so materials that considerably yield are typically called ductile, and those that show little or no yielding at all are called brittle. So the type of qualitatively stress-strain curves that are going to distinguish these two material behaviors, so if it is ductile, what you expect is in both cases, this is going to be stress, this is going to be your strain. you take your specimen and you pull on it. And the stress-strain curve goes up to a certain point, probably elastically, that's what I expect. And after a while, it starts to deform plastically, and at some point, it will break apart. We're going to discuss the exact nature of the stress-strain curve in our next topic as well. But if there is considerable yielding deviation from this initial elastic behavior, that would be called a ductile material. But if the stress-strain curve goes like this, purely elastically, and then with little or no plasticity, the curve abrupts suddenly, and the specimen breaks apart, that would be a brittle material, just like, for instance, a piece of glass. Okay, so these are idealizations, and that's what we want to deal with. And as I said, our goal at this stage is to determine when this is going to happen. Okay, I'm not going to be interested in what happens beyond that point. So we're just interested in predicting the limit to this zone. And that limit is going to be naturally predicted in terms of the stress, the maximum stress that I can apply. So this is going to be our limit in terms of stress to the elastic zone. And this is, for a brittle material, the limit. And if I reach that limit, then our material is about to fail. If I have a design that indicates I'm beyond that limit, that's not a good design. I cannot sustain that stress that is beyond that limit. If my stresses are lower than that limit, then I am safe in both cases. So that's what we are trying to address. Now, however, the difficulty, as I said, is when I have a loading for a structure in which there are multiple stresses present, not only in one direction, but possibly in all directions, in addition to shear stresses, perhaps normal and shear stresses. And that's the case of combined stresses. And let us try to imagine what might happen in that scenario for a ductile material. So we're going to look at a number of special cases, and we are going to assume, as an example, a ductile material, as I said, plus elastic, perfectly plastic material behavior. Okay. What that means is the following. So I am going to take a 4 instances of a block of such material. Okay, and let's draw these blocks first. So it's the same material, and the only thing that will ultimately change is the way we will load that material. So this is not necessarily an infinitesimal piece from a point in a structure. It is in itself a cubic block of metal, if you like. And then we are going to load the structure, and in all cases we will have the same coordinate system. And in the first case, we're going to load it only in the y direction. Goes without saying there's a sigma y in the other direction. Let me draw our coordinate system. In all cases, this is x, y, z. Okay. And what I will additionally draw underneath each curve is the stress-strain curve that I expect to extract from this test. Now, the stress-strain curve is typically done in a uniaxial setting. And if we have multiple directions of loading, the question is which stress and strain shall we monitor? Is there a way to monitor all of them at the same time? There are multiple answers to this question. What we are going to do at the present case is always to monitor the strain in the y direction versus, if you like, the strain versus the stress in the y direction. So stress versus strain curve will have to do with the y direction in this particular case. Okay, so this is the first scenario that we are going to look at. So it is a uniaxial scenario. I do have some understanding of what will happen, and I will first pull on the material. It will start deforming elastically, and there will be a point that will be reached at which those elastic deformations stop. Now, up to that point, the slope in the stress-strain curve will, from our test, will reveal the Young's modulus. All right, so that's the definition of the Young's modulus. After this point, something will happen. Now, because it's ductile, I know that it's going to yield to some extent. Now, how that curve goes, it's going to deviate from a straight line. How it goes depends on the type of plastic behavior. Here we are assuming perfect plasticity, which means that it's an idealized case where the curve goes straight. Well, really, I am not so much interested in how exactly it goes. What I'm really interested in at this stage is simply this limit. This limit where there is a deviation from the initial straight line. So I would expect this line to go forever in that direction, but it doesn't. There is failure. So for our design purposes now, perhaps this indicates failure, and that failure limit to the stress is called the yield strength of the material, sigma naught. So for a ductile material, the yield strength would be sigma naught. We are looking at a ductile material in all cases. In the case of a brittle material, we are going to call that limit to the stress the ultimate stress of the material. Okay, so this is for yield, and in this case, this has to do with the ultimate strength of the material. Okay, because it's just a different terminology since we don't have yielding. Okay, back to that example. So this way we define the yield strength of the material. If it were brittle, then we define the ultimate strength of the material along with its Young's modulus. So that's the case for a uniaxial loading scenario. Now, okay, that's the uniaxial loading scenario. Yield strength, as we know, it's a material property. So the question is, how do I make use of that material property eventually to estimate when yielding occurs in a more complicated loading scenario where we have not only a stress in the axial direction, in the y direction in this case, but a compressive stress sigma x that is equal to the magnitude of sigma y, but because it's compressive, it is negative in value. All right. Well, actually two things happen, and one of these things is something that we are already familiar with. So the first thing that will happen is we are going to start from zero stress and strain, and we will start loading that structure. And I already know that the slope that I measure is actually not going to be the same as the slope that I had measured earlier, which defines the Young's modulus. Okay, and if you want to think about that for a second, I'll give you time, right? But if you pause the video, then you can remember at this stage that generalized Hooke's law can help us predict the Young's modulus of sigma y versus EY in this particular case. And in fact, earlier we called it, just to make a distinction, a different variable. Let's call it E prime again. And E prime is the slope of y versus sigma y versus epsilon y, but it's not the Young's modulus because it is a multi-axial loading scenario. That's what it's going to come out to be in the present case. So the Young's modulus changes. Now, because the Young's modulus changes, I might already suspect that the extent to the elastic zone, the border to the elastic zone, in other words, where it starts, deformation stop to become elastic, will eventually also change, or it might. Now, indeed, that's what happens. The curve doesn't go like this forever. At some point, the curve starts to become, again, because I'm assuming perfect plasticity, it becomes flat again. Now, does it become flat at the point that I encountered earlier? It turns out no, it doesn't become flat at the same value, but rather at approximately half the value. So apparently the presence of the axial stress along the x direction in addition to the one in the y direction reduced the amount of stress I could apply in that direction by almost a factor of 2. So a multi-axial loading scenario induces not only a different stress strain curve with respect to y, which is a direct outcome of generalized Hooke's law, but really more importantly, the maximum stress I could apply in that direction has also changed. So multi-axial loading is certainly giving a different prediction in some sense to the extent of the elastic zone than the uniaxial scenario. Now, the extent of the elastic zone is eventually a material property, and therefore the limit looks different because I don't know yet how to rigorously identify or quantify or eventually formulate that limit. You will see ultimately when we make a clean formulation of the limit to the elastic domain, in other words, the limit beyond which something else happens, plasticity or a fracture, that criterion will not depend on how many stresses you have and eventually whether you have, let's say, only normal and shear stresses, etc., or their magnitudes. There will be a single formulation, a criterion, for instance, that for all loading scenarios is applicable in the same fashion. So, but just at this stage, it seems that the presence of multi-axial stresses is going to give a different sort of failure stress, at least with respect to the value of sigma y. So we can do the same thing for a slightly, again, different scenario. And then in this case, we are going to pull in both directions. So sigma x is equal to sigma y. So we've only changed x from being compressive to tensile. And again, you can remember from generalized Hooke's law that the slope is again going to change, and that slope is going to be equal to, and these are things you may wish to verify yourselves, it's E prime equals E over 1 minus nu. And you might ask yourself, well, does that curve go elastically forever? No, the material is going to start to yield at some point. It's going to fail. And that's the limit. And it turns out that for that case, these are all idealizations of the perfectly plastic behavior. And it turns out that that limit is equal to sigma naught. Okay? So these are not exact. There are factors that eventually in a multi-axial loading scenario will deliver us exactly what that value is. Here we're trying to motivate mainly the point that multi-axial loading will ultimately influence the limiting value of the stress. Now, interestingly, the values are the same in these two cases. All right. Now, all I've done is I've changed the stress from being compressive to tensile. So interestingly, therefore, whether there is a compressive sigma x does change the limiting stress, but if it's tensile, it doesn't, if it is of the same magnitude as sigma y. So just another level of complication. So if I want to predict whether yielding happens or not for some strange, complicated combined stress scenario, I need to have a criterion, a formulation, an algorithm that takes in all of those values of the stresses and is able to predict whether yielding occurs or not. And that criterion should faithfully and correctly predict at least these two or these three simple experiments that I am doing. In fact, if we include the first one, all four of them, right? So let's put yet another one. So in this particular case, we are going to take the material, again, this is an idealization, and we're going to compress it. in a way that the stresses are the same in every direction. And let's call it minus P. We understand that P is pressure greater than 0, so that's a compressive hydrostatic state of stress. And then you start loading the material. And in this case, the slope is E over 1 minus 2 nu. And, well, again, you would expect that there will eventually be some limit to the extent of plastic deformation. It turns out there isn't. You keep loading, 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 and the material just simply does not fail. It keeps deforming elastically. At least it does so up to reasonably very, very large stresses. So, strangely, I now notice that if I have a state of hydrostatic stress for a ductile material, I don't get yielding, right? So, this is the difficulty with combined stresses. You can get a failure at a certain stress, at a different stress, for some entirely different scenario at the same stress, or no failure at all. So how do I address all of these scenarios, all of these, let's say, experimental observations by formulating a criterion, a model that would eventually be able to predict whether failure occurs or not? Now, why do I need models? Why do I need criterions? Well, just like in the case of elasticity, you give me a certain stress, I'd like to predict the deformations. Why? Because in the design process, I have perhaps limitations on the amount of elastic deformations, and I don't want the structure to deform more than a certain amount. Why would I be interested in yielding? Well, in a uniaxial loading scenario, by carrying out the tensile test, I can determine the value of the yield strength. Okay, good. So now suppose this is aluminum and I build a car out of aluminum and it has a complicated state of loading at a certain stage when you drive it at, say, high speed, and you like to know whether some point on the hull of the car there is yielding or not, right? And that point in the metal structure is not going to be subjected to a simple state of uniaxial stress. There will be a complicated state of stress. And you don't want yielding to occur, because if it yields, the stresses are too high, the shape of the hull of the car will simply be deformed out of shape, right? And nobody wants that. So yielding sometimes can mean, in fact, many design scenarios, it means failure. You don't want yielding to occur, and certainly you don't want fracture to occur. So we would like to have models that can predict what happens in the elastic zone and be able to also predict, on top of that, the limit to that elastic deformation. And that is the purpose of this topic.